So your unit exams are marked. You saw your marks, I'm assuming. Overall, very well done. I don't remember the average. I didn't take note of it, but a couple of people got 100, a couple of people got 95. A lot of marks in the 80s, a lot of marks in the 70s. A couple of people didn't do so well. If you are looking at rewriting that, the rewrites would be Tuesday and Thursday of next week after school. Okay. You will get a chance later on today to take a look at your exam. And you know me, I don't stand up here and go over the exams question by question. That's your responsibility to find time to do that. We're moving on today to the second to last unit. It is a relatively short unit, I think 10 days in total. I think the way I looked at the calendar, that final week of classes before our Christmas break, you'll write the exam on the Wednesday of that day. I don't know whether that's a seminar day or not, it doesn't matter. And then on the Thursday and Friday of that day, I think we still have classes on the Friday. We will get started on the final unit, which is considerably different than the entire rest of the course. In this unit, we're dealing with two things. We're dealing with rational functions, which is chapter 9. And then we're dealing with something called function operations, which is chapter 10. So on page 1 of your unit handout, we're going to be dealing with section 9.1 today, which deals with rational functions and transformations. The first item of interest here is that you need to know everything there is to know about y equals 1 over x as a graph. And you also need to know everything there is to know about y equals 1 over x squared as a graph. The reason for that is if you know what that graph or those graphs look like, it's pretty basic to tell me about transformations of those graphs and what those transformations would look like. You know, and just briefly here, the very first kind of complicated function that you learned about in high school math was y equals x squared last year in Math 20-1, but then you immediately started talking about transforming it. And you used parameters last year like p and q, whereas we use h and k. And you also talked in a limited way about a, about multiplying y equals x squared by some number and the fact that it could reflect it or stretch it. But that should be old hat to you, which means it should be second nature to you now. We don't often talk about this, but you could take a very basic linear function like y equals 1 over x and apply a, b, h, and k to it. By the way, you'll notice when I talked here about what you did with quadratic functions last year, I didn't use a b because you didn't use b last year. And there's a reason for that. With quadratic functions, it gets quite confusing by including a b. But we could apply a, b, h, and k to a very basic linear function, y equals x. Last year, you learned about this function, y equals the absolute value of x. You weren't really taught about applying transformations to it. But again, if I gave you the following, you ought to be able to tell me the changes that would occur to the graph that you're looking at right now based on a, b, h, and k. Make it a little easier. A is -2, which means that this original graph will be reflected vertically and stretched vertically by a factor of 2. B is 3, which means after that happens, the graph is going to be stretched horizontally by a factor of 1/3. H is 3, because you have to factor that 3 out of the 3x minus 9 to put it in the A f of b bracket x minus h plus k form. So you need to explicitly factor that 3 out, and then you can see that h is 3, which would mean we shift it 3 to the right, and then we shift the result 11 units up. And this is all review, and as I said, it should be really second nature. In the last unit, we learned what y equals 2 to the x looks like. It's a basic exponential function. You now should be able to transform that through the application of those 4 parameters, a, b, h, and k. Another exponential function, but this one has a base between 0 and 1 as opposed to greater than 1. We've learned, and I think this was actually in the first unit, what y equals root x looks like. There's an arrow on the end of these graphs, so they don't just stop. Although this one does start at the origin. You should be familiar with that, so you can apply transformations. Sine, well, you can apply a, b, c, and d to it. We don't use h and k for sine, we use c and d. I hope you're getting the idea that throughout the past couple years, you've learned of a lot of functions that you could apply transformations to. Logarithmic. Well, to summarize the whole point of this introduction, today what we're looking at is being able to transform y equals 1 over x. So you need to know what that looks like. You need to know what that looks like much in the same way that you know y equals x squared is a parabola that opens up with its vertex at the origin. It's knowledge. And you also need to know what 1 over x squared looks like. So to begin with, as a warm-up, I'm going to introduce the idea of a rational function. And by the way, the function 1 over x, y equals 1 over x, you did learn about last year, but you called it a reciprocal function, which we're going to toss that idea away this year. It's too limited. What a rational function is any function that is equal to the quotient of 2 functions. Okay? So I'm saying f of x is a rational function if it can be written as n of x over d of x. N stands for numerator, d stands for denominator. We don't have to use those letters, I'm just using them. So n of x and d of x are polynomial functions, but the denominator function cannot be 0 because you can't divide by 0. Now this is the textbook definition, not just in our textbook, but in any textbook, and I think there's a flaw in it. And the flaw is that the denominator has to be at least degree 1. If you look at what a polynomial function is 5 a polynomial function? Yes, it is. It's a polynomial function of degree 0. And what I'm telling you is this definition, I believe, is flawed because according to this definition, something like 3x squared plus 2 over 5 is considered a rational function, and it's not. The idea here is that since the denominator isn't variable, it's not considered a rational function. I like this better. A rational function has to be a function that's written as a fraction where the bottom depends on x in some way. The top can be a degree 0 function, but the bottom cannot be a degree 0 function. So generally speaking, you know you have a rational function if, and there's conditions to it that I don't want to get into, but if when you write it in fractional form you see x or the independent variable in the denominator. So these two functions, f of x equals 1 over x and f of x equals 1 over x squared, are both rational functions, and I consider them to be very basic rational functions. I don't know if I used the word base in your notes. I suspect I changed it to basic, correct? Yeah. Later on in your notes, I do use the word base. I decided before I printed this out last night to change the word from base to basic because I didn't want you to think this has anything to do with exponents. Okay? This has nothing to do with bases of exponents. I'm just saying this is the building block for rational functions. So what we are asked to do is sketch f of x equals 1 over x on our graphing calculator, draw a picture of it, and then describe the properties of this. Now it turns out that you learned about this function last year in Math 20-1. But I'll try to tie that way of thinking of this that you did last year to what we're going to be doing this year. So this is a very simple function to enter. We're going to enter y equals 1 over x. We typically choose zoom standard. That's probably a good thing to do. Although I'm going to say we're going to do something different in a second. And you get this kind of picture. Now, depending on your window settings, well, no, we already went zoom standard. When you go zoom standard, what your graphing calculator does is it goes from -10 to 10 horizontally and from -10 to 10 vertically. But what that means, since your window is wider, physically your window is wider than it is tall, the distance from -10 to 10 horizontally is stretched out more than the distance from -10 to 10 vertically. And we can get away from that by choosing zoom square. Now what zoom square does is it rescales the axes so that a physical distance on your calculator screen of 5 horizontally is the same as a physical distance on your screen of 5 vertically. So we get a slightly different picture of it. We get a fairer picture. When we scale grids and we draw graphs in math, we generally don't use a different scale horizontally as vertically. And we do that so that things are scaled properly. The horses are not really tall, like if you're watching a movie and they've compressed the screen into a 4x3 letterbox screen where the horses and the cowboys are tall. Everything is the way it appears. So what we get is this general shape. Both of these curves are symmetric, well, to each other, but they're also symmetric relative to the axes. In fact, this one up top, I maybe drew a little too steep. Both of these curves, I did it again. Both of these curves are symmetric with respect to the axes. What I'm getting at is, and I don't want you to draw this, but if you drew the line y equals x in here, which is a line at a 45-degree angle, it would slice each of those two arcs into mirror images. As well, they're identical except they're in different quadrants. Now, if you consider the behavior of this graph y equals 1 over x, and you don't have to write this down. In fact, you know what? I'm not even going to write it down. I'm going to go to my graphing calculator. And I'm going to go to my table, and I think my table has already been set up to start at 0. Well, I'm moving it to 0 now. To start at 0 and go up by 1. So first of all, when x is 0, we cannot calculate a y coordinate, and that should be plain due to the fact that y is 1 over x. And if x is 0 and you try to take 1 divided by 0, it doesn't work. You're not allowed to divide by 0. What that means is that looking up here, x is allowed to be, 3 or 4 or 5 or a million. X is allowed to be 0.002, just a number. X is allowed to take on those negative values as well. X can be any number, and now we're going to put the domain here. Any number that is not equal to 0. And we can call that a non-permissible value. Clearly, x cannot be equal to 0 because the denominator of this function is 0, and you cannot divide by 0. Another way that you could write that domain is to say that x is an element of the union of the numbers from -infinity up to 0 but not including 0 with the set of numbers from 0 but not including 0 up to positive infinity. I mean, these are just different ways that you could write the domain. I'm not a big fan of sprinkling the parsley on the fish and saying, oh, and by the way, x is a real number, but you might see that on a diploma exam. What does that translate to physically? If we were to go to very, very small values of x, and the behavior of the graph I'm talking about here, although it's a very simple graph, is very important for everything we do in the next couple of days. what is the behavior of y, of the function, at very small values of x? Well, can I take with this function y equals 1 over x? I think I said 0.02, didn't I? I think. Can I take 1 divided by 0.02? I can, but I get a fairly large y-coordinate. And when you take a look at the graph here, immediately to the right of the y-axis, the graph is curving up. It's pointing towards the sky. And that's because as x gets smaller and smaller and smaller, am I allowed to take x divided x equal to 0.0003? Sure. The y-coordinate would be 1 divided by that number, which is now we're in the thousands. And since there's no limit to how close I can get to 0, there's no limit to how high this graph goes. That graph goes up towards infinity, and no matter how close it is to the x-axis, or to the y-axis, no matter how close it gets to the y-axis, it will continue to go up. And that is referred to as an asymptote. One of what I think is the funniest words in math. And it's a vertical asymptote. So because x cannot equal 0, but it can equal anything to the left and the right, we draw that dotted line in. That dotted line is not really part of the graph of the function. It's just showing you some place where the function can't be. By the way, as x gets closer to 0 from the left side, the graph will take off to negative infinity. Now, what about the behavior? We talked about the behavior when x is very, very tiny and close to 0 on either side. What about the behavior when x is very large? So I can go to my table now again. And I can start scrolling. I'm keeping my eye on the behavior of the function, which is y, as x gets bigger. As x gets bigger and bigger and bigger, you can see y getting smaller and smaller, which is the nature of a reciprocal of a number, which is what you kind of use that idea in 20-1. Is there any limit to how big x can be? No. And if y is getting smaller and smaller as x gets bigger and bigger, then there's no limit to how small y can get. But it will always be a non-zero number. One way to look at it is if you're going to take the number 1 and divide by something, you will never get 0 because the top is 1. The only way a fraction can be 0 is if the top of the fraction is 0. What this means is at very large values of x, the function approaches 0. And that's another asymptote, and that's a horizontal asymptote. And every function that you dealt with that had this kind of nature to it last year, the horizontal asymptote was always the x-axis, and that's not going to be the case this year. We already have our domain written down. Let's write our range now. Our range would be y is not equal to 0 as well. This is a very difficult thing for some people to understand. It's an interesting thing that when you look at the vertical nature of this graph, it goes up to infinity and the bottom goes down to negative infinity. And the bottom half of the graph always climbs higher and higher. And the top half always gets lower and lower, no matter how far out you go. But the bottom will always get higher and higher but never reach y equals 0. The top will get lower and lower but never reach y equals 0. So y cannot equal 0. It's kind of the same idea as what we said for the domain. We could also put the ranges from negative infinity down at negative infinity towards the floor, up to but not including 0, in union with not including 0 up to positive infinity. I don't think there's anything more we need to describe. We can't talk about x or y intercepts because since the x and y axes are the asymptotes, the graph never touches that. Now, let's take a look at y equals 1 over x squared. Since y, before we put this in the calculator, since y is 1 divided by something squared, you will never get a negative y. You can't get a negative y because the bottom is always going to be positive. For the same reason that we talked about with the previous graph, if you have 1 divided by something, it doesn't matter what the bottom is. That thing can never be 0 because the top would have to be 0. Along the same lines as the previous graph, if x were 0, not the whole thing, but if x were 0, well, you would be dividing by 0 because 0 squared is 0. And that must mean x is not allowed to be 0 as well, which means we can start off and we can say that the domain as x is not allowed to be 0 and the range as y is not allowed to be 0. But y equals 1 over x had a piece, that's just a note for me, had a piece in quadrant 1 and a piece in quadrant 3. Now that piece in quadrant 3 had y coordinates that were all negative. But we're squaring x here. We're taking 1 divided by x squared. So we would expect that all these y coordinates that were down in quadrant 3, that were 1 over x, are going to become positive. They're going to jump up top. It's not a reflection, but they will go up top. So let's take a look at what it looks like now. Y is equal to 1 over x squared. It looks like that. Now, one of the things you will notice is that there's a lack of symmetry with each curve. The two curves themselves are symmetrical. I'm going to change the window settings here. These two curves are symmetrical to each other, but they don't have a symmetry like this curve has, where this and this are the same. The difference with y equals 1 over x squared is that these graphs are steeper. There is a reason for that. It's because when you square a number, it becomes more extreme. I didn't say bigger, because we know when you square some numbers, they get smaller if they're less than 1. So if you take 0.01 and you square it, you get 0.00001, I think. You get 3 zeros and then a 1. And when you take 1 over that, it gets bigger, but it gets bigger by an even greater factor. It's not exponential, it's quadratic, but it gets bigger by an even greater amount than it would if you didn't square it. So those lines go up quite steeply. They also drop quite rapidly because when you go to x equals, say, 10, instead of getting 1 over 10 for y, you get 1 over 100, so it really falls. One thing I forgot to point out, and I meant to, is that these 2 points are key points and are at 1, 1 and -1, -1. They're fairly significant points because the reciprocal of 1 is 1, 1 over 1 is 1, and when x is -1, 1 over -1 gives you the y coordinate, you get -1. For that reason, we still have points here at 1, 1, and this point will be at -1, 1. And you can, cast your gaze up here to the function and ask yourself what happens if you put 1 in for x. You're going to get 1 for y. If you put -1 in for x, you're going to get 1 for y. There is something else that I suppose we should have done. This is the domain and range. A domain tells you what x is allowed or not allowed to be. And since there's only one value that x can't be, it's a lot simpler for me to just write x can't be that number. The range tells you the values of y that are allowed, or in this case, we can just say everything except for y equals 0. But we didn't write the equations of the horizontal asymptote or of the vertical asymptote. And I think that's an important thing to talk briefly about here. What are the equations of these two asymptotes? So the horizontal asymptote is this line right here. And that line has an equation of y equals 0. Because, again, this is y equals 1, this is y equals 2, this is y equals 3, this is y equals -1, -2, -3. This is where y equals 0. Any point on the x-axis has a y coordinate of 0. There's a really subtle difference here between what I write for the equation of that horizontal asymptote and what I write for the range. Well, it's not really subtle, but it's one that can be subtle in your head if you don't think about it. If I say, where is the asymptote, you're going to say it's at y equals 0. If I say, what is the range, you're going to say, well, since there's an asymptote at y equals 0, y can't equal 0. That's a little tricky. The vertical asymptote is at x equals 0, and these two equations for the asymptotes would be the same for this graph. They would have to be. They're the same locations. So this is, the horizontal is at y equals 0, the vertical is at x equals 0. And I'm going to pause there and ask if anybody has any questions with those two sets of graphs. All right. So if you applied a, b, h, and k to 1 over x, I'll just cut to the chase here. If you apply a, b, h, and k to 1 over x, that's what the function is going to look like. Except we don't include a b. If I did include a b, please don't write this, we would also have that. Because the function is 1 over x, f of b times x minus h would be 1 over b times x minus h. I don't really want to explain why we don't use it other than to say if we included a b, things get quite complicated. And really, it's the same reason you didn't include a b with parabolas last year. The basic reason is that a can handle all stretches, horizontally and vertically. If you apply your a, h, and k to 1 over x squared as a function, in other words, you're doing this, y equals f of b bracket x minus h n bracket m bracket plus k, then this would go into the function, and the function is 1 over x squared, so we have 1 over, and I included b again out of habit, we're not including b. This would go in for x in the original function. The function is 1 over x squared, so we get 1 over x minus h squared. We multiply it by a, and I'm on a roll here because I forgot my a. We multiply that by a, so you're going to have a times 1 over x minus h quantity squared, and then you're going to add k. I guess in the end, you need to recognize that these two functions on the right are products of doing something to the two functions on the left. Does that make sense? Okay, well, let's find out. Let's do a couple of questions together. Sketch the graph of y equals 6 over x minus 2 and then minus 3. So we need to sketch the graph of y equals 6 over x minus 2 and then minus 3. You should see this as a variation or a transformation of 1 over x. The x becomes x minus 2, which means that h is equal to 2. The 1 over the x minus 2 becomes 6 over x minus 2, which means we're multiplying by 6. So a has a value of 6. And then afterwards, you're subtracting 3, and that means that k is equal to negative 3. Remember, with the x, it's x minus h, so the number itself is the opposite of h. Now, don't draw anything just yet. If you start off with y equals 1 over x, this is where the asymptotes are. Follow this logic carefully. It's the same logic that we used for graphing transformations of trig functions. Will either of those asymptotes move if things are stretched or reflected in any direction? No. So whatever happens in terms of A is not going to affect those asymptotes. After A is applied, though, those asymptotes will move. Because if I'm going to shift the entire graph 2 units to the right, because h is 2, that asymptote is going to be over at 2. That vertical asymptote is going to be shifted to 2. If whatever happens after I stretch things is then shifted 3 units down, and the stretching doesn't move the horizontal asymptote, then after that stretch occurs, this asymptote will be down at negative 3. I'm telling you that the asymptotes will always be related to h and k. And I got to think about this, which means you should have to think about it. The vertical asymptote is always going to be located at x equals h. The horizontal will always be located at y equals k. Now, imagine that where these intersect is the origin. It's not. We know that. But 1 over x has a key point at 1, 1, and it has a negative 1, negative 1 key point. That 6 is going to stretch those 2 key points 6 times further away from the x-axis. Are you with me? But that means they get stretched 6 times further away from the horizontal asymptote. You can feel free to plot those 2 points, stretch them vertically by a factor of 6, and then shift them 2 to the right and 3 down. Or you can say, I know the asymptotes are here. These key points would be here and here without a stretch. 1 to the right and 1 above the intersection of the asymptotes. 1 to the left and 1 below. But if I stretch them by a factor of 6, this point is going to be 6 times further away, which means it will be 6 away. Which is an interesting thing that I'm basically telling you the value of A is going to be how far away the point will be from the horizontal asymptote if the point is 1 to the left or 1 to the right of the vertical asymptote. I mean, let's face it, the coordinates of this point are actually 3, 3, not 1, 6. This point is going to be stretched 6 times further away from the horizontal asymptote, which means it will be 6 away. We're not moving at 6. We're stretching it by a factor of 6. I suppose we should find the X-Intercept, because that will give us more texture to what we draw, rather than, I mean, let's face it, don't draw this, but you could just go, okay, I think it looks like this and like this. But I don't know how well I've drawn it. I think we should find the intercepts, which just is a matter of applying some math that you learned in grade 9 or 10. Our function is y equals 6 over x minus 2 minus 3. To find a y-intercept, we let x equal 0. To find an x-intercept, we let y equal 0. The y-intercept is pretty easy because it's already rearranged for y. We'll have 6 over 0 minus 2 minus 3. And you can work that out for me, please. I think it's going to be negative 6. So the y-intercept is at 0, comma, negative 6. Well, that's pretty useful. Now it's kind of giving us an idea of how steep this curve needs to be. The x-intercept we are going to let y equal 0, so we'll have 0 equals 6 over x minus 2 minus 3. I would probably move the 3 to the other side and get 3 equals 6 over x minus 2. Multiply both sides by x minus 2 to get this. And I know, when I teach math 10 and 20, there's a couple of ways to go about this. I don't think you should multiply that 3 through. You can. You can multiply it through and solve it from there. But why don't you just divide both sides by 3 first to get x minus 2 equals 6 over 3 is 2. So the x-intercept is at 4, comma 0. And again, I'm doing this so that we get a little bit more, as I say, texture to this. Otherwise, I don't know if I'm drawing it as steep as I should. I would say at this point, if you drew this, as long as the curve, let me finish this before I speak, as long as the curve is asymptotic to both asymptotes, I looked it up, that actually is a word. Asymptotic means behaving like curves do next to asymptotes. Getting closer. And that's it. Domain and range. X is not equal to 2. Range, y is not equal to negative 3. Sorry, my brain stalled there for a second. Is this always going to be x is not equal to h? Yes. For these functions, okay? Not for some of the other ones we'll look at in this unit. The equations of the asymptotes would be y equals negative 3 and x equals positive 2. And we've got the y-intercept and the x-intercept, so we're done. Any questions with that example? All right, sketch the graph of y equals 2x plus 2 over x minus 4. So this is tricky. This is a variation of 1 over x. And I know it's a variation of 1 over x because it's over x minus 4. I don't see any squareds there. But it is not in the right form. We need to get this into y equals a number over x minus a number plus a number to decide what the transformations are. There are two ways to do this. I'm not a fan of what the textbook does. I'll maybe show it to you in a bit. But what I'm going to do is I'm going to do synthetic division. I'm going to take the polynomial 2x plus 2 and divide by x minus 4. So 2x plus 2 divided by x minus 4. And remember, this is a good thing to review. When you do synthetic division, which you need to know for the diploma exam, the number that goes to the left of your template is the 0 of what you're dividing by. And we bring the first number down and then we proceed. You take 4 times 2 and it gives you 8. You add 2 and 8 and get 10. What does that mean? It means that this is the quotient. It's the result of the division, and this is the remainder. And the division algorithm, which is what it's called, the rule that connects the divisor and the dividend and the quotient and the remainder, leads us to this conclusion that y is equal to the division of these two, which gives us 2, plus the remainder over what you were dividing by. And then it's a matter of, switching the order that we wrote these two terms in and saying 10 over x minus 4 plus 2. You can now see that a is 10, h is 4, k is 2. That means we can take y equals 1 over x, shift the vertical asymptote over to 4, shift the horizontal asymptote up to 2, then take the key point that's 1 to the left and 1 below the intersection, and 1 to the right and 1 above the intersection of those asymptotes, and stretch them vertically from the asymptote by a factor of 10. So this is y equals 10 over x minus 4 plus 2. Let's get our asymptotes in there. We're going to have an asymptote, a vertical one at 4. Does this graph match your graph? Okay, thank you. And we're going to have a horizontal asymptote at 2. Had there been no vertical stretch, these would be the key points, because that would be at 1, 1 if those asymptotes were at the origin. We're kind of cheating the system here by doing shifts before we do stretches. But since a is 10, and I should have written this, a is equal to 10, h is equal to 4, k is equal to 2. Since a is 10, it's going to be 10 times further away. These points will each be 10 times further away from that horizontal asymptote. Which means if it's 1 away and it's at, I guess this is 3, it has to be 10 away, which would be at 12. So you really have to think here carefully. You could count the squares, and I would actually be more comfortable counting the squares. There should be 10 squares there. I didn't do it by counting the squares, but I think that's more foolproof. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And this one, 2, 3, 4, 5, 6, 7, 8, 9, 10. Will there be an X and a Y-intercept? Well, not up here. Not in the top right corner. But there should be down in the bottom left corner. I think it's easier to find, maybe, the X and Y intercepts from this. That's a matter of preference, I guess. I would be more comfortable just going with this to find the X and Y intercepts. If you let y equal 0, this will be an important thing later. I'm not actually going to rearrange this for x. If this rational function that we're looking at, which is a fraction, is equal to 0, the only way that can happen is if the top of the fraction is equal to 0. Which means the x-intercept is at -2. In other words, this will be the rule I'll give you tomorrow, I think. If you want to find x-intercepts, look at the zeros of the numerator. Question, Liam? Thank you. -1. Yes, well, I didn't. I should have factored a 2 out of the 2. And I'm left with x plus 1, which means that I'm going to have an x-intercept of -1. My apologies. The y-intercept, well, the y-intercept is pretty easy. All you're going to do for the y-intercept is put 0 in for x. By my count, I get negative 1/2. Get 2 on the top, negative 4 on the bottom. So the x-intercept is negative 1. The y-intercept is negative 1/2. At least this is giving us some idea of where this curve is going, right? If I didn't have those 2 points, I might be inclined to just do this, which isn't very accurate. Oop. And then you can kind of mimic this over here. It doesn't have to be perfect. That's good enough. You can write out the domain and range if you want. The domain would be x is not equal to 4. The range would be y is not equal to 2. You could also write out the equations of the asymptotes, but I think you get the idea. I think we have one last example we are going to look at here. Example 3. So we have 3 functions, f of x, which is 1 over x squared, g of x, which is a different function, and h of x, which is a third function. And it turns out that you can get g of x from f of x. I'm going to give you a minute to think about how. I don't know if anybody will get this. I hope some of you do. Do you have it, Evan? Okay. You have it? The idea here is that, Evan, you want to volunteer what your thoughts are?
Sure, you're looking for g of x, right?
Yes.
Denominator of g of x is quadratic. And since it's not the difference of squares because it has a degree 1 term,
Correct?
which is what we're looking for, right? So it can be written as x minus 5 squared.
Right. Perfect. It's quadratic, so we look at the possibility of factoring. It's not a difference of squares because it's got that linear term, that minus 10x. And what Evan's saying is when he factors this, he gets x minus 5 squared. Keep something in mind. X minus 5 squared means x minus 5 times x minus 5. And when you factor x squared minus 10x plus 25, you're looking for 2 numbers that multiply to give 25 and add to give negative 10. So it's minus 5 and minus 5. And now you can see if you go from f of x, which is 1 over x squared, to g of x, which is 1 over x minus 5 squared, the only change is that you've taken 5 away from x, which means you've introduced an h value in relation to the original function of 5. So the answer to the question is take f of x and shift it 5 units to the right to get g of x. I don't know how you want to abbreviate that, but I will remind you. Oh, and there's also a 3 there, isn't it? I will remind you, though, on a written response, you would have to write it out in words. There is a 3, which is an h or an a of 3. So there's a vertical stretch. By a factor of 3. And, you know, the vertical stretch happens first, realistically, but if we were to sketch it, we could always shift the asymptotes and then stretch it relative to the asymptote. Why don't we do that? We are asked to sketch these, so let's sketch this one first before we go on. Is this the graph that you have? Pretty much? Okay. So the asymptote pair would be in this location before any transformations. For g of x, we shift things eventually 5 to the right, which means this will be where the asymptote is, the vertical asymptote. Going back to the base rational function of y equals 1 over x squared, and I don't know that you want to draw this or not, the base rational function of 1 over x squared has these two key points, and it's fairly steep. Those two key points are both 1 away from the horizontal asymptote. So if I stretch them vertically by a factor of 3, they would be 3 away from the horizontal asymptote. And that means when I shift the whole graph 5 to the right, they are still going to be 1 to the left and 1 to the right of the vertical asymptote, but they will be stretched vertically away from the horizontal one by a factor of 3. Boy, there's a lot of words in what I just said. You got to really think carefully about what you're writing or saying or thinking. So again, I don't want to necessarily put that in there. I just want to say that it will be here and here, 3 away from the horizontal asymptote. So this is what it will look like, very roughly. No X and Y intercepts, so we're done. We're done with that. This is g of x. I think h of x, for the second part of this final example, I think this is more obvious. I'm not entirely sure that you need to do everything I'm going to show you to see what a, h, and k are. I can rewrite this as negative of 1 over x plus 4 squared plus 6. I can take that negative and throw it on top with the 1. And now I can see that we're dealing with a equals negative 1, h equals 4, k equals 6. Questions with that? Pardon me? Didn't I put negative 4? Oh, I didn't. Did I say negative 4? I guess not. It is definitely negative 4. Thank you, Mackay. It is definitely negative 4. So we are going to shift this parabola, or this, it's actually called a hyperbola. This graph, we're going to end up shifting it 4 to the left and 6 up. But it's going to be reflected before that happens. Even though it's reflected before that happens, I'm going to do the shifts and then ask myself where it would end up relative to those asymptotes. So for h of x, the vertical asymptote will be at negative 4. Was it 6 units up? The horizontal asymptote will be up at 6. And if there was no reflection, 1 over x squared would have these points in relation to those asymptotes. But it's reflected vertically, and it's reflected vertically before we do this. But reflecting it vertically will put these points below the x-axis, which is where the asymptote is. So when we move the whole thing, it's like we're moving the x-axis, but we're only moving the asymptote. So what this is going to look like is the following. There are going to be a couple of x-intercepts, which I'm not interested in solving for, because I'm guessing it's going to require the quadratic formula, and that's not the point of this lesson. If you took that original function, set y equal to 0, and started rearranging for x, you would end up with a quadratic equation. Any questions with the final example 3? Okay. Just a note here on the practice problem set, not 15 and 16. And this isn't even a case of, well, if you want to try them, try them. I recommend that you don't even look at them. Sketches are not required. So, so what is it I want you to practice if you see a question that says sketch the graph? I want you to be able to tell me everything about the graph, where the asymptotes are, whether it points up or down, what the domain is, what the range is. If you feel really ambitious, you can find X and Y intercepts. You should be able to find out everything about these. You have about 16 minutes left. I'm going to hand back your exams so you can at least take a look at them. And tomorrow we're going to move on and look at something that moves away from transformations.